Hello friends, welcome to the lecture on stream gauging. So far we have seen various methods for measurement of discharge through a stream. In this lecture we are going to deal with one more method, that is the slope area method, to find out or to estimate the discharge flowing through a stream. So let us start. Look at the diagram. The diagram represents two different sections separated by length L of a stream. This bottom represents the datum, and this vertical line is the section 1, and this is the section 2 separated by distance L. This is the datum Z1 for section 1, datum Z2 for section 2, and Y1, Y2 represents the height of the particular water surface. So here in general, with respect to datum, you can consider the height of flow for section 1 as Z1 plus Y1 is equal to H1, and for section 2 from datum it is Z2 plus Y2, that is H2. This is the velocity head for section 1, V1 square by 2g, and it is V2 square by 2g at section 2. From section 1 to section 2, there is head loss. If you consider a straight horizontal line showing the energy, then you can see that there is a head loss from section 1 to section 2. This head loss can be represented by this particular depth, that is total head loss. This head loss is split into two different head losses, that is HE, head loss due to eddies, and this is HF, that is frictional head loss. So after understanding this is the direction of flow. After understanding these are two sections and a different application of Bernoulli's equation for the continuity, let us find out how to measure the discharge. The resistance equation for uniform flow in an open channel example, Manning's formula can be used to relate the depths at either end so far each to the discharge. In simple words, we are going to apply Manning's formula to find out the discharge by using this particular figure. Figure shows the longitudinal section of flow in a river between two sections, section 1 and 2. Knowing the water surface elevations at two sections, it is required to estimate the discharge. Applying the energy equation to section 1 and 2, Z1 plus Y1 plus V1 square by 2g, Z1 plus Y1 plus V1 square by 2g is equal to Z2 plus Y2 plus V2 square by 2g plus H suffix L, where H suffix L is the head loss in the reach. It is the total head loss, which is splitted into HE and HF further. The head loss H suffix small l, capital L, can be considered to be made up of two parts. One is frictional head loss HF, which is shown over here, and second is the eddy loss, that is HE. Denoting Z plus Y as H, this Z1 plus Y1 as H1 and Z2 plus Y2 as H2. Water surface elevation above datum, we can rewrite this particular equation by substituting Z1 plus Y1 as H1 and Z2 plus Y2 as H2. Here H1 plus V1 square by 2g is equal to H2 plus V2 square by 2g plus HE plus HF. By rearranging, we can get HF is equal to H1 minus H2 plus into bracket V1 square by 2g minus V2 square by 2g minus HE, denoting it as equation A. This is head loss due to friction. If L is the length of the reach, by Manning's formula for uniform flow, HF upon L is equal to SF, that is the energy slope, is equal to Q square by K square. HF upon L is equal to SF, which is energy slope, which is further equal to Q square by K square, where K is conveyance of the channel, which is equal to 1 upon N A into R raised to 2 by 3. This K is different for different section. For section 1, K value will be different depending upon the characteristic like area, Manning's coefficient, and weighted perimeter, that is R. We have to calculate while solving the problem. We have to calculate the value of K at section 1 and section 2, and with the help of a formula we find out only one value of K, as K is equal to under root of K1 into K2. In a non-uniform flow, an average conveyance is used to estimate the average energy slope, and HF upon L is equal to SF, that is energy slope, is equal to Q square upon K square, where K is under root of K1 into K2, as already I have stated, and K1 is equal to 1 upon N1 A1 into R1 raised to 2 by 3, and K2 is equal to 1 upon N2 A2 R2 raised to 2 by 3, where N is the Manning's roughness coefficient. The eddy loss H suffix E can be estimated as it is equal to Ke into V1 square upon 2G minus V2 square upon 2G, where K suffix E is the eddy loss coefficient having values as below. Eddy loss coefficient generally depends upon the cross-sectional characteristics of the reach. If there is no change into the cross section from section 1 to section 2, that means the section is uniform from section 1 to section 2. There is no expansion, no contraction, then the value of K suffix E will be 0, and ultimately the value of this eddy loss will also be 0. If there is gradual transition, then for expansion value of Ke will be 0.3, and for contraction it will be 0.1. And if there is abrupt transition, means sudden change into the cross sectional area from section 1 to section 2, then there will be more eddy formation and there will be more eddy losses. Therefore, for sudden change, for expansion from section 1 to 2, the value of Ke will be 0.8, and for contraction it will be 0.6. Now look at the equation A, B and C. Equation A is for finding out the head loss, frictional head loss. B is to find out the energy slope, which also has head loss, length, discharge and conveyance of the channel. And equation C has head loss due to AD, which also has eddy loss coefficient. So by equation A, B and C together, and with the continuity equation Q is equal to A1 V1 is equal to A2 V2, enable the discharge Q to be estimated for known values of H, channel cross sectional properties and N. That means if you know the value of H, if you know the channel cross sectional properties like area, weighted perimeter and Manning's constant, you can find out the discharge by using earlier equations A, B and C. The discharge is calculated by a trial and error procedure using the following sequence of calculations. Assume V1 is equal to V2. This leads to V1 square by 2G, that is velocity head at section 1, is equal to V2 square by 2G, that is velocity head at section 2. And by equation A, what is equation A? Here, this total term will be 0, isn't it? By equation A, HF is equal to H1 minus H2 is equal to F is equal to fall in the water surface between section 1 and 2. Using equation B, calculate discharge Q. When once you get HF, you can find out by using this particular formula, you can find out the discharge. Compute V1 is equal to Q upon A1 and V2 is equal to Q upon A2. Calculate the velocity heads and eddy loss HE. Now calculate a refined value of HF once again by equation A and go to the step number 2. Repeat the calculations till two successive calculations give values of discharge or HF differing by a negligible margin. This method of estimating discharge is known as the slope area method. It is very versatile indirect method of discharge estimation and requires the selection of a reach in which cross-sectional properties including bed elevations are known at its ends. The value of Manning's N and water surface elevations at two end section, they must be known to work out the slope area method. With the help of an example, we will understand how to estimate the discharge by using this slope area method. Now read the example. During a flood flow, the depth of water in a 10-meter wide rectangular channel was found to be 3 meter and 2.9 meter at two sections 200 meter apart. The drop in water surface elevation was found to be 0.12 meter. Assuming the Manning's coefficient to be 0.025, estimate the flood discharge through the channel. So let us understand the problem first of all. During a flood flow, there is a flow, the depth of water in a 10-meter wide rectangular channel. So the shape of the channel is rectangular having width equal to 10 meter, and depth of water at section 1 it is 3 meter and depth of water at section 2 it is 2.9 meter. The sections are separated by a distance capital L is equal to 200 meters. The drop in the water surface elevation was found to be 0.12 meter. This is the head loss. Assuming Manning's coefficient small n is equal to 0.025, estimate the flood discharge through the channel. Now as a part of solution, using suffixes 1 and 2 to denote the upstream and downstream sections respectively, the cross-sectional properties are calculated as shown in the table. So for section 1, the value of y1 will be 3 meter. For section 2, value of y2 will be 2.9 meter. A is the area of cross section for section 1, that is 30 meter square. Since 10 into 3 it will be 30 meter square, and for section 2 it will be 29 meter square, isn't it? So P1 will be equal to 16 meter and P2 will be 15.8 meter. P1 will be 16 meter and P2 will be 15.8 meter. These are the perimeters. R1 is the weighted perimeter or hydraulic mean depth. For section 1 it will be A1 upon P1, which will come out as 1.875, and for section 2 it will be A2 upon P2, that is 1.835. Now values of K1 and K2 are calculated based on the formula 1 upon n into A1 into R raised to 2 by 3, and K2 is equal to 1 upon A2, sorry, 1 upon N into A2 into R2 raised to 2 by 3, which is coming out as K1 is equal to 1824.7 and K2 is 1738.9. Then the average value of K for the reach will be equal to under root of K1 K2 is equal to 1781.3. To start with, HF is equal to fall, that is head loss, is equal to 0.12 meter. It is assumed. AD loss HE is equal to 0. The calculations are shown in the following table. So let us see how the calculations are done. Here SF is equal to HF upon L, so which is further equal to HF upon 200. Q it is equal to K under root of SF is equal to 1781.3 under root of SF. V1 square upon 2G is equal to Q upon 30 whole bracket square divided by 19.62. V2 square upon 2G is equal to Q upon 29 whole bracket square divided by 19.62. Therefore, HF is equal to H1 minus H2 plus into bracket V1 square by 2G minus V2 square by 2G. HF is equal to fall plus V1 square upon 2G minus V2 square by 2G is equal to fall, that means the head loss, that is 0.12 plus V1 square upon 2G minus V2 square upon 2G. So this is what the estimation of head loss due to friction. Now look at the table for trial 1. Let us see the table first of all. Column number 1 represents the trial. There are 3 trials taken. HF for each trial, head loss due to friction for each trial. SF, then Q, discharge meter cube per second, then V1 square upon 2G, that is velocity head, V2 square upon 2G, then HF by equation which is stated over here. For trial number 1, HF it is 0.12 meters. If you consider this 0.12 meters, then SF comes out as 6 discharge 43.63, V1 square 0.1078, V2 square upon 2G 0.1154, and HF comes out as 0.1124. If you go on iterating by different trials, you will come to know that the value of discharge, it stables somewhere in trial 2 and 3, and here you can get the head loss due to friction as a constant value. So after third trial we stop the iteration, and the last column HF you can find out by this equation E1, and its value is adopted for the next trial every time. This HF for first calculation it is adopted for the second, it is adopted for the third. The discharge in the channel by these trial and error method, it has come up as 42.32 meter cube per second. So I request all of you to go such one kind of numerical through the standard reference books. If you find anything difficult, you can ask me on my email address dnpaitankar@sanjeevani.org.in. Thank you for listening. Happy learning.